after adding or after inserting nodes in the left side. So we can call it left skewed tree because all the nodes are in the left subtree. So if all the nodes are in the left subtree, we have to shift some nodes from the left subtree to the right subtree. So which rotation now should be used? Obviously, right rotation. Using this right rotation, now we can shift some nodes from the left subtree to the right subtree. And in this tree, 10 is the first node, so it should be moved first. 10 will be shifted to the right side. It will become the right child of a node. And now the middle node is 7. After moving this, the first node, now 7 will become the root node. That means 10 is the right child of 7. And 7 already has a left child, so 5 is the left child of 7. So when we apply that right rotation, when the tree is a left skewed tree, all the nodes are in the left side, that's why we applied right rotation. So now calculate the balance factor. For all these nodes, all these three nodes, the balance factor is 0. That means this is a balanced tree. And is this a BST? Yes, the left child is less than 7, less than the root node, and the right child is greater than 7. So it's a binary search tree. So is it clear when we can apply the right rotation?
For now, yes, ma'am.
Okay.
Ma'am, is it like that if we face the LL, that means we have to do the decisions like RR?
Yeah, we always use the opposite one.
Okay, ma'am, got it.
We are always using the opposite one. Okay, so now the structure is like this. At first we are taking 5, and now how we can insert 7? 7 is greater than 5, so add it in the right side. Now calculate the balance factor. For 7, the balance factor is 0, and for 5, the balance factor is -1. Because in the left subtree is 0, so 0 minus 1 equals to -1. Now if we insert another node 10, where will insert it? In the right subtree. After inserting the node, now calculate the balance factor. For 10, 0, 7 -1, but for 5, the balance factor is -2. The height of the left subtree is 0, and the height of the right subtree is 2. 0 minus 2 equals to -2. That means this is not a balanced tree. Okay, so how to make it balanced tree? If we shift some nodes from the right side to the left side, then maybe the tree will be a balanced tree. Okay, so here all the nodes are added in the right side, so we need a left rotation for moving some data, some node from the right side to the left side. This is the left subtree. Okay, so now how we can, which node will be shifted? The first one, the root node. So now 5 will be shifted in the left subtree. It will be left child of the root node 7. Now 7 is the root node, and 7 already has a right child 10. So when we use this left rotation, when all the nodes are in the right side. Clear?
Yes, ma'am, got it.
Okay, so now the next one is right, left, or left, right. So when to use this rotation? After adding some nodes in the left subtree and in the right subtree, if the balance factor is more than 1, then we have to apply RL or LR. Okay, so now suppose the first node is 12. This is a root node. So we can insert it here, and its balance factor is 0. Now, the next node is 5. Is it less than 12? Yes. So why will insert it in the left subtree? After inserting 5, now calculate the balance factor. For 12, the balance factor is 1, and for 5, the balance factor is 0. And now the next node is 17. In which side will insert it?
The right side.
In the right side, because 17 is greater than 12. So after inserting another node, calculate the balance factor. 5 and 7 are leaf nodes. Their balance factors are 0. 12 has exactly one left child and one right child. So their heights are same. So the balance factor will be 0. Okay. So now after that, we are adding another node, that is 7. So in which side will insert that node?
The left side.
Left side.
7 is less than 12, so add it in the left subtree, but 7 is greater than 5. Okay, so we'll add it here. Now calculate the balance factor. For 7 and 17, the balance factor is a 0. For 5, it's -1. For 12, the balance factor is 1. So is this a balanced tree?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay, so now the next node is 6. So why to insert that node? Here in the left
Left
side.
side.
Now calculate the balance factor. The balance factor of 6 and 17 is 0. For 7, it's 1. Now for 5, the balance factor is -2. Right? 5, now the balance factor is -2 because in the left subtree the height is 0, in the right subtree the height is 2. 0 minus 2 equals to -2. So now this is the infected node, or we have to change this portion of the tree. So how we got this tree? After taking a right child first and then by taking a left child. This is the right child, 7 is the right child of 5 and 6 is the left child of 7. Right. So now here at first we will change the leaf node, this portion. So we'll always use the opposite rotation. After adding a left child, we can see that here the balance factor is more than 1. So for changing this one, we need to use the opposite rotation. That means right rotation. At first we'll work on this part and then we will change this one. So here we got 7 by adding a right child in where? To the root node 5. 7 is the right child of 5. So if it is right child, then we should use which rotation? Left rotation. Okay, so at first we'll change this portion of the tree by using right rotation. Right, that means shift some nodes from the left side to the right side. 7 and 6. So how we can apply the right rotation? 7 will be shifted to the right side and 6 will become the root node. Okay, that means 6 is the root node and 7 is the right child of that node, and there is the root node 5. Is this a right skewed tree? Yes, because all the nodes are in the right side. So now apply left rotation. So now 5 will be shifted to the left side and 6 will become the root node. So 5 is the left child of 6 and 7 is the right child of 6. So, okay, so now this is the balanced tree. So is it clear when we can use right left rotation?
Yes, ma'am.
When the sequence is like this, right left. But at first we'll work on this part from the left node. Okay, so I hope now it's clear to you how to insert node in a wheel tree. So can we start the next operation, that is deletion?
Yes, ma'am.
Okay. So suppose some nodes are given and we constructed an AVL tree. That means that tree is BST, binary tree, as well as a balanced tree. Okay. 20 is root node, and in the left subtree there are some nodes 13. Okay, the right child is 27. The left child of 13 is 6. The right child is 15. 27. The left child is 25. The right child is 38. It's just 2. The right child 9. Choice is 18. 38 has a child and the right child. So now look at the tree. Is it AVL tree? At first we'll check whether it is BST and then we'll calculate. So is it BST? Look at the left subtree. Here all the nodes are less than the root node 20. And in the right subtree, all the nodes are greater than 20. That means it's a BST. Is it balanced tree? There are some leaf nodes 2, 9, 18, 21, 30, 40. For these leaf nodes, the balance factor is 0. 6, 30, 27, 38. They exactly have two child. One is left child, another is right child. So their balance factor will be 0. Look at the 6. The height of the left subtree is 1 and the height of the right subtree is 1. 1 minus 1 equals to 0. The same for 13. 13 has 2 left child. I mean, in the left subtree, the height is 2. In the right subtree, the height is also 2. For 13 and 27, it's 0. What about the root node? For 20, the height of the left subtree is 3 as well as the right subtree. So its balance factor is also 0. And 15, 25, these nodes have one child. So its balance factor for 15, the balance factor is minus 1. For 25, the balance factor is 1. That means this tree is a balanced tree. So we can call it a real tree. Right?
Yes, ma'am.
We know the process. We know how to insert the nodes in a real tree. After taking one node, after inserting one node, we have to check the balance factor. If it's a balanced tree, then it's okay. It's an a real tree. Otherwise, you have to make it balanced tree. But now, from this tree, how we can delete some nodes? Can you remember how we deleted some nodes in binary search tree? Suppose this is a binary search tree. 30 is the root node, and 20 is the left child, 40 is the right child, and 20 has one left node, that is 10. So this is a binary search tree, right? And there are three cases for deleting some nodes in binary search tree. The first case is we can delete a node with 0 child, we can delete a node with 1 child, or we can delete a node with 2 children. And here, when a node has 2 children, we can take the in order successor or in order predecessor, isn't it? So how we can delete this 10? 10 is a leaf node. We can simply delete that node from the tree. Okay, so now suppose we want to delete 20. So 20 is a node with 1 child. How we can delete it? After deleting that node, we can add each child node where to its parent node. After deleting 20 now, 10 will become the left child of 30. Okay. And what about the node with 2 child? If we want to delete this root node 30, how to delete it? We can take a node from its in order successor, or we can take in order predecessor. Right, so here if we want to take in order predecessor, how to choose a node from left subtree. In order successor, that means we are going to take a node from the left subtree. So which node will be taken? The node with the highest value, isn't it? Hello. How to select a node from in order predecessor? In order predecessor, that means this is left child is placed before root node, so left subtree is the predecessor for root node and right subtree is the successor. Just 24, 32. And then 10 has another child, 5. So this is now the left subtree for 30 and this is the right subtree. Okay, so how we can choose a node from in order predecessor? In order predecessor, that means choose a node from the left subtree. Which one? There are 4 nodes. Which one will be selected as a new root node? The highest one. So here 24 is the largest node, so we'll replace the root node with that node 24. So 24 will be deleted from the left subtree and then we'll make it the root node of the tree. So now look at this. After replacing the root node with its in order predecessor, now is it a binary search tree? Yes, because all the nodes in the left subtree are less than that node, and in the right subtree, all the nodes value are higher than 24. That means we can take in order predecessor or we can take in order successor. What is in order successor? Take a node from the right subtree. So in the right subtree, there are two nodes. Which one will be taken? Now the smallest one. Within these two nodes, which one has the smallest value? 32. So now we can replace the root node by this node 32. Just delete the node from the right subtree and then replace it with the root node. In this way, we can take in order successor from this tree. Is it clear? We discussed those things in binary search tree, deletion of binary search tree. So this AVL tree is a binary search tree. So we'll apply the same process for deleting the nodes. So in AVL tree, if we want to delete some nodes from the tree, we can have how many options, how many choices we have? 3 choices. We can delete a node with 0 child, or we can delete a node with 1 child, or we can delete a node with 2 children. Suppose this is the sequence. We want to delete the node 9 first, then 6, 13, 20, 25. So the first node is 9. Now identify that node in the AVL tree. So this node 9, does it have any left child or right child? No. This is a node with 0 child. So how to delete that node? Is simply delete that node from the tree. The node 9 doesn't have any child node, that's why we can simply delete it from the tree. But this is not only binary search tree, this is AVL tree. After deleting that node, now we have to check whether the tree is balanced tree or not. When there was a node 9, at that time the balance factor for 6 was 0. But after deleting 9, now calculate the balance factor. All the balance factor, the balance factor for all these nodes will be same, only its balance factor will be changed, right? So what is the balance factor of 6? The height of the left subtree is 1, and now the right subtree is empty. So 1 minus 0 equals to 1. After deleting 9 from this tree, now you can say that this tree is a balanced tree. So this is an AVL tree, right? Hello? Okay, so now we want to delete the next node 6. So where you can find that node 6? This one. Now the node has 1 children. And how we usually delete a node from binary search tree with 1 children? After deleting that node, we add its child node to its parent node. That means after deleting 6 from this tree, we will add the left child of 6 as the left child of 13. So now we will delete 6 from the tree and 2 will be shifted here. 2 now become the left child of 13. Okay, so after deleting 6 from the tree, again calculate and count the balance factor. For 2, 18, 21, 30, 40, balance factor is 0. 13 has 2, how many child in the left subtree? Only 1 node. So the height of the left subtree is 1, but in the right subtree the height is 2. So 1 minus 2 equals to minus 1. What about 25? The height, the balance factor of 25 is still 1. For 38, the balance factor is 0. For 27, the heights are same. 2 minus 2 equals to 0. For the root node 20, in the left subtree, the height is 3. And in the right subtree, the height is also 3. So the balance factor is 0. That means after deleting another node from the tree, it's also, it's still a balanced tree. So we can call it AVL tree. Okay. Now the next one, delete 13 from this tree. Where is 13? This one. Now 13 has how many child? 2 children. One is left child, that is 2, and another is 15. So there are 2 options for deleting a node with 2 child. You can take in order predecessor or you can take in order successor, which means that you can select a node from the left subtree or from the right subtree. But if you want to take the in order predecessor, then take the largest one, the node with the highest value. Or if you want to take the successor node, then take the smallest one from the right subtree. So here in the left subtree, there is only 1 node 2. So we can simply replace that root node with in order predecessor. Okay, so now 13 is, I'm writing it here. So 20 is the root node. After deleting 13 from this tree, now 2 is the left child of 20. That means the right child 15 will be assigned to the node 2. 15 will be assigned where? As the right child of 2. And 15 has a right child, that is 18. And in the right subtree, the nodes will be added as your in the previous one. So 27, 25 is the left child, 38, 25 has one left child, 21. For 38, there are two child, 30 and 40. Now after deleting 13 from this tree, now calculate the balance factor. The balance factor of these nodes in the right subtree will be same, because we made some changes in the left subtree. Okay, so now the balance factor of 15 is still -1. But what about this one? 2 doesn't have any left child. So it's in 0 minus 2, very good. 0 minus 3 equals to -2. So the balance factor of 2 is -2. So is it a balanced tree now? No. And which one is the infected node? 2. That means we have to change this portion of the tree. So how to change it? Look at this. Oh, very good. Left rotation, because this is right skew tree. So we can shift to in the right side, then we can make 15 the root node of the tree. So can I delete this one, this figure?
Yes, ma'am.
Hello?
Yes, ma'am, you can.
Okay. So now how will apply the left rotation? Apply LL, that is left rotation. So this is our infected area, that is 2, 15, 8, 18. So after applying left rotation, some nodes will be shifted to the left side. Okay, so now 2 will become the left child of 15 and 18 is the right child of 15. Okay, so in the new tree now we'll add this portion. 20 is the root node, and now the left child of 20 is 15. So 15 is the left child and it has child 2 and 18. The right child of 20 is 27. Left child of 27 is 25. For 27, it's 38. 25 has a left child 21. 38 has a left child 30 and a right child 40. Okay. After deleting 13, the tree After deleting 13, we got this structure, isn't it? And this tree or this node made the whole tree unbalanced. That's why we applied which rotation? Left rotation, and now we got this structure. Now calculate the balance factor. For 2, 18, 21, 30, 40, the balance factor is 0. For 15, the balance factor is 0. For 27, the height of the left subtree and right subtree are equal, so its balance factor is 0. For 20, of the left subtree is 2, but the height of the right subtree is 3. So 2 minus 3 goes to -1. So this is a balanced tree. Now we'll delete the next node, that is 20. Okay, so identify the position of 20 or how many child that node has. Where is 20?
The root one.
The root node. Now 20 is the root node, and this is the left subtree for 20 and this is the right subtree. So 20 is the node with 2 child, so we can take a child from its left subtree or from the right subtree. So if we want to take a node from the left subtree, which one we should choose?
15.
The largest one. So 18 is the largest node. So we'll replace 20 by 18. So now, if we want to delete 20, we have to replace it by a node from its left subtree or from the right subtree. Now we'll replace it with a node of the left subtree, that is 18, because 18 is the highest one. So now the root node is 18 and its left child is 15, and 15 has only a left child 2, and the right subtree, the right child is 27, and its children are 25, 38, 21, 30, and 40. Now calculate the balance factor. After deleting 20, is it a balanced tree?
Yes, ma'am.
For 2, 21, 30, and 40, balance factor is 0. For 15, the balance factor is 1. For 27, 0. For 80, minus 1. So this is the balanced tree. Now delete 25. 25 is a node with one child. So we can simply delete that node from the tree, and then we can assign that child 21 where? In the left subtree of 27. So after deleting 25, here we'll add 21. Now again calculate the balance factor. For 27, the balance factor is minus 1. But still the tree is a balanced tree, as well as it's a BST, binary search tree. That means this is an aerial tree. So is it clear how to delete some nodes from the aerial tree?
Yes, ma'am.
Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes. I want to know from all of you, is it clear?
Yes, ma'am.
Yes, ma'am. Okay, so in this topic, we mainly discussed about balanced tree. What is balanced tree? The difference between the left subtree, the height of the left subtree and right subtree cannot be more than 1. That is balanced tree. And what is an aerial tree? It's one kind of binary search tree and a balanced tree. That means after inserting a node or after deleting a node, we have to measure the balance factor. If the balance factor is within that range minus 101, that means the tree is an aerial tree. Otherwise, we have to change its structure by using the rotation left, right, or right, left. So that was aerial tree. Okay, so now the next one. There is another tree which is called heap tree. Okay, so now we'll discuss a new tree, that is heap. Okay, so how many trees so far we discussed? At first a general tree, and then binary tree. What is binary tree? A node can have 0, 1 or 2 children, but not more than 2. That is binary tree. Look at this. 20, 10, 5, 2, 7, 18. So is it a binary tree?
No, ma'am.
Why not?
5, 18 on the right side, which are smaller than 20.
Don't get confused. I'm not talking about BST. It's not BST, it's only binary tree.
Oh.
And it's a binary tree. In binary tree, we don't actually compare the value of the child node with the value of the root node. This is just a binary tree. Why it's a binary tree? Because here each node has exactly 0 child, 1 child, or 2 child, but not more than 2.
Yes, ma'am. Got it.
20 and 10 has 2 children, 2, 7, 18 has 0 children, and 5 has only 1 child. It's a binary tree.
Yes, ma'am.
And what is general tree? A node can have more than 2 child, that is general tree. Then what is full binary tree? Full binary tree is when in each level there is exactly 2 to the power L number of nodes. Suppose 20 is the root node. So in full binary tree, each node should have exactly 2 child. So 20 has 2 child, 10 and 5. 10 also has 2 child, 2, 7, and 5 has 2 children, 12 and 18. So this is a full binary tree because each node has exactly how many child to children. This is full binary tree. Okay, so now we know that the first level number is always 0, this level 1, and this level 2. In full binary tree, we can assign some values. Suppose this is the first node of the tree, the node number is 2, 3, 4, 5, 6, and 7. And in full binary tree, we know that in each level there would be total how many nodes? 2 to the power L number of nodes. So in the first level, L equals to 0. So it has how many nodes? 2 to the power 0 equals to 1, exactly 1 node. In the second level, the L equals to 1. So the second level has exactly 2 nodes, 10 and 5. In the third level, L equals to 2. So the third level has exactly 4 nodes. And if I take another child here, that means at that time the level number will be 3. And if it's full binary tree, then the fourth level should have how many nodes? 2 to the power 3 equals to 8 node. That is full binary tree. Okay, and there is another kind of tree which is called complete binary tree. So what is complete binary tree? Complete binary tree is one kind of binary tree. Okay, each node should have how many child? Exactly 2 child except the last level. What does it mean? Look at this full tree. I'm reading this figure. What is the difference between a full binary tree and a complete binary tree? In full binary tree, each node should have 2 children, and in each level there should be 2 to the power L number of nodes. So suppose this is a full binary tree. Is this a last level? No, because there is one more level, and the nodes are 2, 7. And now suppose the 5, this node 5 doesn't have any children, it's a leaf node. So can we call it full binary tree? No, but we can call it complete tree, complete binary tree. Why? Because only the last level is incomplete. This level has exactly 2 to the power L number of nodes, and the same for the next level. But here, this level is supposed to have 4 nodes, but it has only 2 nodes, and this is the last level of the tree. That's why we can call it complete binary tree. Okay, and another property, of this full binary tree or complete binary tree is without adding a left child to a node, we can't add a right child. Suppose here, we can't add 18 before taking a left child. At first, we have to take a left child for 5, and then we can add a right child. And this is same for complete tree. What I said, in complete tree, only the last level can be incomplete. That means without filling this level, we can't take a level in the next level. We can't take a node in the next level. It's impossible. Or suppose 5 doesn't have any left child, but we have added a node in the right child. It's not a complete binary tree. Still, it's a binary tree. So is this clear? What is binary tree, what is full binary tree, and what is complete binary tree?
Yes, ma'am.
Yes, ma'am. Clear, ma'am.
Okay. And this is not binary search tree because we are not comparing the node value. Okay, we can add any values in the left side or in the right subtree. Okay, so now how we can define heap? It's another type of tree. So heap should be a complete binary tree. What is heap? It's not BST, but it's a complete binary tree. Okay, so suppose the first node of the tree is 40. The root node is 40. Okay. After that, if we want to add a node and if its value is 30, why will we add it? Do we need to compare it? No, it's not binary search tree. But still, in the child node should be less than 40. In the left subtree, we can take the largest one, 35. In the right subtree, we can take the lowest one. It's not a problem. But in heap tree, the value of the root node should be always greater than its left child and the right child. Is it clear what is heap tree? This is one kind of complete binary tree. That means all the level except the last level should have 2 to the power L number of nodes. So I'm taking another level, and if 35 is the root node, and if its child value are 31, 27, okay, and for 30 if its value is 27 and 28. Now look at the tree. 40 is the parent of 35 and 30, and here 40 is greater than its child node, right? And 35 is the parent node of 31 and 32, and its value is greater than its child node. Okay, what about this one? 30 is a parent node of 27 and 28, and its child value are less than 30. So we can call it a heap tree, and when the root node is greater than its child node, it's called max heap tree. What is the name of this heap tree? Max heap. And it's not mandatory to take a full binary tree. I already told you, if the tree is a complete tree, we can call it heap tree. Okay, so there are two types of heap tree. One is called max heap and another is min heap. So this tree is max heap because the root node is greater than its child node. So it's called max heap. So what is min heap? Min heap opposite of max heap. In min heap, the value of root node is always less than the value of its child node. So here 10 is the parent node of 40 and 50. So here the root node is smaller than its child node. That means it's min heap tree. And then 40 is the parent node, and it's a min heap. So it's child value 70, 60. Okay, so this is a min heap tree. So now if I take a data here, suppose the right child of 50 is 80. So now can we call it min heap tree? Is it min heap tree? Hello? Is it minimum heap tree?
No.
How? I already explained you the concept of complete binary tree. In complete binary tree, without taking the left child, you can't add a right child. If that node doesn't have any left child, how you can add a right child? This is complete binary tree. So at that time, we can just call it a general tree or a binary tree. This is just a binary tree, not max heap tree, because it's not a complete tree. In complete tree, always you have to fill up the left child of a node, then you can add a right child. Is it clear what is the concept of complete binary tree and max heap or min heap tree? This heap tree is a complete binary tree. That means always we have to fill up the left side first, and then you can add the nodes in the right subtree. That is complete binary tree as well as heap tree. And when we can call a heap tree as maximum heap tree, when the root node has the highest value than its child node. And minimum heap tree is when the root node has, or the root node is less than its child node. Is it clear?
Yes, ma'am.
Okay. So now we can use any one of this, max heap or min heap. Suppose you want to create a max heap. That means the root node should be greater than the child node. Okay. So think about this one. This is I already told you a binary tree. Full binary tree has exactly how many nodes in each level to the power L number of nodes. This is just a binary tree, not heap tree. This is a binary tree. How many nodes each level has to the power L number of nodes. So now, if we want to store this tree in an array, is it possible? Yes, because if we want to add the index here, it will be the first node of the tree. So its index is 1, 2, 3, 4, 5, 6, 7. So we can easily insert all those nodes in an array. Okay, so if we start the ordering from 1, 2, 3, 4, 5, 6, 7. So now we can store the root node in the first location, that is 1. And after that 10, because its index value is 2. Then 30, 15, 12, 11, 7. Okay, that means we can store the node of a full binary tree in an array. And it's possible for a complete binary tree also, because in complete binary tree only the last level is incomplete, and we always take the nodes in the left subtree first and then in the right subtree. So if I remove the node at that time also, we can store them in an array. Okay, so now look at the max heap tree. So there are some nodes for 44, 30, 50, 22, 60, 55, 77, and 52. So we have to insert this tree wire in a max heap tree. We can insert the node wire in a max heap tree. But the condition of this insertion is, the first thing is that max heap should be a complete binary tree and the parent node should be greater than its child node. So initially the tree is empty, so we can insert the first node, that is 44. 44 is the first node. Okay, so after inserting 44, we got this structure. Now the second case, when we have to insert the next node, that is 30. So compare 30 with 44. Is it greater than 44? We need to compare it first, or at first we have to insert it. This is max heap, so here we don't need to compare whether that value is less than 40. It's not binary search tree. In binary search tree, 30 is less than 44. That means we'll add it in the right subtree, or in the left subtree. Where? In the left subtree. But this is not binary search tree. This is a max heap tree, or we are just trying to create a complete binary tree where at first the left child should be filled up. So always we'll add child in the left side, in the left subtree. So after inserting 30, now compare it with the root node. 44 is the parent node of 30 and it's greater than 30. So that means it's a max heap tree. Okay, now after that we will insert 50. This is level 0 and this level is exactly one node. This is level 2, but the level number is actually 1. This is level 1, where the maximum number of node is 2. That means the next node will be inserted where? In the right side of 44. So this is 30, and after inserting 50 in the right side, now compare it. No, because the parent node is less than the right child. So how we can make it max heap tree?
We can take 50 as a child of 30.
This is a complete binary tree. Okay, or think about this one. Suppose this is our array. Initially the array is empty. After inserting a node 44, now we have inserted in the first location 1. When the representation of array will be like this. The first node is 44, and then we can insert the second node in the next memory location, that is 30. Okay, so now the next node is 50. So after inserting that node in the tree as well as in the array, so 1, 2, so we'll insert it in this position, 44, 30, and 50. Now look at the tree. 55 is greater than 44, so it's not max heap tree. How we can change the look? How we can change the value? Change the node. We cannot randomly just change the nodes. If it is a tree, 44, 30, 50. Okay. Think about in this way. This is the max heap tree, so 50 is the largest one, and its left child is 30. And right child is 40. So this is the max tree where the root node is greater than its child node. Okay, and the index 1 is 2, 3. And how we can insert these nodes in an array? At 1, and then the second node is 30, and then the third node is 40. 20. Where will insert it? Here. right? 20, and suppose 30 has another node that is 25, so we'll insert it in the array after 20. Okay, so in the from the tree we can easily find out which one is the parent node of which child node. Here 30 is the parent node of 20, 25, but from this array how you can identify the parent node and the child node. Suppose 50 is the parent node. We want to find out which node from these array are the child node of 50. How you can find it out? By using this equation. For left child, if k equals to 1, then 2k it's the value of its left child and 2k plus 1 is the position of its right child. So when k equals to 1, 2 into 1 equals to 2. That means 30 is the left child of 50 and 2k plus 1. When k equals to 1, 2 into 1 equals to 2, 2 plus 1 equals to 3. So 40 is the right child of 50. Is it clear? If we want to find out the child node of any parent node, we can use this formula. For finding the position of left child, use 2k. For right child, 2k plus 1. Okay, suppose 30. 30 is now the root node or parent node. So which one is its child node? What is the position of 30? 2. That means k equals to 2. So 2k equals to 2 into 2 equals to 4. So go to that location 4. 20 is the left child of 30, isn't it? And what about the right child? 2k plus 1. When k equals to 2, 2 into 2 equals to 4. 4 plus 1 equals to 5. So 25 is the right child of 30. Is it clear how to find out the left child or right child of a node?
Yes, ma'am.
Okay. So why we actually need it? Because without identifying the child node or parent node, we cannot interchange these nodes. Okay, so here after inserting a node in this position 3, now the array has 3 nodes and 50 is the right child of, it's a right child of 44. We can say it from the tree. Okay, but when we have only this array, how we can identify it? How we can find out its parent node? Here I equals to 3. I is a pointer. After inserting a new node, this pointer value will be increased by 1. Okay, so when I equals to 2, that means it's denoting to the node 30. Okay, so when we inserted another node in this position, that means the value of I was increased. Now I equals to 3. Okay, so for that node, how we can find out its parent node? If the parent node is given, you can easily find out the left child and right child, isn't it? By using this equation 2k and 2k plus 1. So when the child node is given, how you can find out its parent node? Just divide that pointer value by 2. So 3 divided by 2 and take the floor value. What does that mean? 3 divided by 2 equals to 1.5. So if we want to take the floor value, that means we will take 1, not 2. Right? If we want to take the seal value, at that time the pointer value should be 2. So if I equals to 3, that means now the current node is 50. Which one is its parent node? Divide that pointer value by 2 and take the floor value. 3 divided by 2 equals to 1.5. That means floor value is 1. So 40 is the parent node of 50. After that, we will interchange the position of these two nodes. We can simply interchange these two nodes. So now 50 will become the parent node and 44 will become the right child of 50. Is it clear?
Yes, ma'am.
So the time is almost over. So I think we will discuss this topic again in our next class. Okay, but the concept of tree, that is which one is binary tree, which one is complete binary tree, it should be very clear to you. So max heap, it's one kind of complete binary tree. That means without taking the left child, we cannot add a right child. And another thing is, if we are creating a max heap tree, then the root node should be always written in the child node. Clear?
Yes, ma'am.
So we'll continue this topic in our next class.